Welcome back. This is Chapter 1 lecture for an Introduction to Earth Science from the textbook Foundations of Earth Science, the 8th edition. And of course that is by Lutgens and Tarbuck. And this is Matter and Minerals, Chapter 1. Now, most of these lectures end up being quite a number of slides, so I'm going to move through these, or at least try to move through these pretty quickly, so we're not spending an hour and a half on each lecture. We're going to try and keep them at or under an hour for you. So let's just go ahead and get started. In terms of matter and mineral and what we see as a geologist's definition of a mineral, it's naturally occurring. It's an inorganic solid. It's got an orderly crystalline structure. You can see the crystals in this illustration, and it has a definite, very specific chemical composition. And minerals are the building blocks of rocks. Rocks are essentially made up of a conglomerate or a bunch of different minerals, sometimes just one, but typically more than one mineral all kind of stuck together. That makes a rock. So minerals are naturally occurring, formed by natural geologic processes. Synthetic minerals are not considered minerals. They're not naturally occurring. Minerals are generally inorganic. Crystalline solids from organic sources are generally not considered to be minerals. Some organisms actually secrete inorganic compounds like calcium carbonate, and that's considered to be a mineral when they become part of the rock record. So when that calcium carbonate is solidified into a rock or lithified into a rock, then it's considered to be a mineral. And minerals are solid substances. Ice, frozen water, is therefore considered to be a mineral. Liquid water and water vapor, not minerals. All right. So minerals have an orderly crystalline structure. Atoms are arranged in an organized, repetitive manner. So that organization reflects the crystalline shape of the mineral. So in this case, sodium and chloride, you're going to have chlorine atoms surrounding sodium atoms in this very structured cubic-like organization, and therefore your sodium chloride is going to come out as a cube-shaped. And so that's the crystalline structure. So minerals have an orderly crystalline structure. They have a very specific chemical composition. It does allow for some variation, but typically your minerals have a specific chemical combination, and in some cases one element may be substituted for a different element within the mineral, but typically they're the same size, so that doesn't change the crystalline structure. So most minerals are actually compounds, so two different elements together. They can be expressed as a chemical formula. So this is a silicon, quartz, which is made of silica and oxygen. Si is silica and O2 is oxygen, and that is the specific chemical formula or the compound SiO2 of quartz. And again, you can substitute some elements in some minerals for other elements of the same size, and so you have slightly different minerals resulting. All right, a rock is also a naturally occurring solid mass of mineral. It's a mass of mineral, or mineral-like matter in some cases. Most are aggregates or collections of different minerals. In some cases you have just one mineral like gold or copper, but most are aggregates of different minerals. Individual properties of those minerals are retained. So this is a chunk of granite here, and then within this chunk of granite, which is a plutonic igneous rock, it was a melted magma that cooled slowly, creating these large crystal grains. And these crystals are crystals of quartz. These crystals here are crystals of feldspar, and these crystals, the black ones, are crystals of hornblende, or maybe even a mica. But nonetheless, the different minerals maintain their individual properties in this conglomerate of rock. Now, some rocks are composed of a single mineral. Limestone, for instance, is the mineral calcite, which is calcium carbonate. That's the formula, calcium and carbonate and carbon dioxide together. So that is a mineral, that's a rock, that's a single mineral. And then some rocks are made of non-mineral matter. Obsidian and pumice are actually glass. They're not minerals. The cooling happened so rapidly that the mineral structure did not occur. So they're non-mineral matter. That's a rock, that's a non-mineral matter. And coal, because it's organic, is a rock. That's a non-mineral matter. So all matter that makes up elements, minerals, and rocks, and everything else, all matter, including minerals, matter is composed of atoms. And atoms are the smallest particles that cannot be chemically split. An atom contains three smaller particles, protons, neutrons, and electrons, and they make up the atom. So your protons and your neutrons, which are really, really big at the atomic size, make up your nucleus, and the electrons basically orbit the nucleus in what we refer to as shells. They're not necessarily orbits as we see like a planet orbiting the sun. They're actually shells. They spin around the nucleus. So all matter is made up of these three subatomic particles. The only difference between hydrogen and helium, or hydrogen and lithium, or hydrogen and gold, is the number of protons, neutrons, and electrons. So all matter is made up of the same subatomic stuff. It's just the number of those protons and neutrons that differentiate between different elements of matter. So all atoms, other than hydrogen and helium, are formed inside stars through nuclear fusion. And the reason why we exclude hydrogen and helium is because hydrogen and helium are thought to have formed in that initial cooling after the expansion of the universe. Of course, the expansion of the universe is what we call the Big Bang. So after the first initial expansion, the cooling that began, hydrogen and helium condensed. Hydrogen and helium all clump together with enough heat and pressure, create nuclear fusion, and it's that nuclear fusion that creates or forms all of the heavier elements beyond hydrogen and helium. All right, protons, neutrons, and electrons. Protons and neutrons have almost identical mass. They're big. Electrons are much, much smaller. Protons have a positive charge, neutrons have no charge, and electrons have a negative charge. And the reason why we have neutrons at all is because protons having a positive charge, protons with a positive charge, something has a like charge, it would repel it themselves, just like two positive ends of a magnet would repel itself. And so in the case of the nucleus that has to be stuck together, you have to have some way for the protons not to repel themselves or move away from themselves, and that is the neutron. The neutrally charged subatomic particle acts as a buffer, so that's what allows the nucleus to stick together. And most matter is neutral because the protons and the electrons cancel themselves out. So if there are 8 protons, the little red guys, then there'll be 8 electrons, and the positive charge of 8 protons and the negative charge of 8 electrons cancels them out, and you end up with a neutrally charged matter. Now, not all matter. Ions have a positive charge or a negative charge, depending on which it has the most of, and we're going to learn lots more about ions as we progress. Electrons are shown to orbit the nucleus, as we see here, but in reality, they kind of spin around it in a cloud. So there are multiple levels of clouds, and the first cloud around the nucleus will only have 2 electrons, and then each subsequent cloud around the nucleus will have as many as 8 electrons. So the first cloud will have 2, the second cloud may have 8 if there's enough actual electrons, and if you have more than 10 electrons, the third cloud may have up to 8. But atoms want to have 8 in that last cloud, sometimes called the valence cloud or valence orbit. And so the reason why atoms stick together to form molecules and sometimes compounds is that attempt to have a stable 8 electrons in that outer cloud. All right, electrons move around the nucleus in a cloud with different regions called shells. So I talked about one shell, a second shell, the first shell having 2 electrons, the next shell having 8 electrons or up to 8 electrons, and the next shell after that having up to 8 electrons. And the more and more electrons and protons that an atom has, the bigger and the heavier that atom is, and that makes, denser minerals. So hydrogen is very light, lead is very heavy because there's just more electrons and protons and neutrons stuck in that atom. Each principal shell has an energy level and a specific number of electrons. The first shell has 2, each subsequent shell can have 8. The outer shell contains what are known as valence electrons, and those interact with the valence electrons of other atoms to make chemical bonds. And we're going to talk about the different types of chemical bonds. The number of protons in the nucleus of an atom gives it its atomic number. All right? We talk about atomic number, that's the number of protons in an atom. It determines the chemical nature of the atom, whether it's hydrogen or helium, and all atoms that have the same atomic number are known as the same element. So all hydrogen atoms have one proton, they're all hydrogen. If an atom that has the same number of protons, if two atoms that have the same number of protons have different number of electrons making them ions, but they're still the same element, they're just different ions of the same element. There are approximately 90 naturally occurring elements, and those elements are arranged on the periodic table. And elements of similar properties line up in columns. So here's a periodic table. There's a lot of really small information here. This is a pretty comprehensive periodic table, but I want to show you that hydrogen has one proton. That's the atomic number. Helium has two protons. That's the atomic number. Lithium, beryllium, boron, carbon, nitrogen, oxygen, they all have the atomic number, the number of protons. So carbon, all carbon can have the same number of protons, but there are slightly different carbons that might have slightly different numbers of electrons, and carbon 14 or carbon 12. And so that's where you get different atoms that are the same element but have different number of electrons. So the symbol of the element, the name of the element, carbon, C is the symbol for carbon, and then the atomic mass. This is the atomic mass. And you can see hydrogen is the lightest atomic mass, 1.008, and then helium is 4.003, and the atomic mass gets heavier and heavier, and you can see heavier elements like gold, 197, right? So gold is 197 times heavier than hydrogen, essentially. And then in here you'll find, you're going to find your lead. Lead is heavier than gold. Silver is going to be, Ag is much lighter than gold, much lighter than lead. But this is the periodic table. And where you have different types of, you have metals in the purple, metalloids, nonmetals over here. There are noble gases. In the end, that's the periodic table. All right. Most minerals are chemical compounds, two or more elements joined together. Some minerals are made up of a single element, like gold or sulfur or copper. And native minerals are when you have pure copper found in nature. It's considered a native mineral. Typically, even minerals that are it's made up of single elements like gold or copper have something in them that does not make them pure. But if you're pure, then it's a native mineral. All right, so we talked about valence electrons. Electrons in that outer shell. The atom wants to have 8 electrons in the outer shell. It can have up to 8. If it doesn't have 8, it's less stable. If it does have 8, it's very stable. So 8 valence electrons in a stable arrangement in a full valence shell. It takes 8, right? The noble gases all have full valence shells, 8 electrons in the outer shell, so they don't react with anything chemically. In order for an element to react with something chemically, have a chemical bond, it has to have less than 8 valence electrons in that outer shell, other than hydrogen or helium, because well, hydrogen only has 1 in its first shell. It could have up to 2. Helium actually has 2, so it's one of those noble gases. As a matter of fact, here are your noble gases. There's 2 electrons in the outer shell of helium. In neon, there's 2 in the inner shell and 8 in the outer shell. In argon, 2 in the inner shell, 8 in the second shell, 8 in the outer shell. So these are all the noble gases. They do not interact with other gases because, again, they have the perfect number of electrons in their outer shell, so they're chemically non-reactive. Right? Elements gain or lose or share electrons during chemical reactions to have that full valence shell. That's what produces stable electron arrangement. So when they chemically bond to a chemical reaction, they're trying to achieve that stable valence shell of 8. Elements, again, other than the noble gases, form bonds under the temperature and pressure conditions that occur here on Earth. And that's how we get these different chemical bonds, these different chemical combinations. Those bonds lower the total energy of the atom and make them more stable. The noble gases are stable. Other elements that don't have 8 in the outer shell, they want to achieve stability through chemical bonds, chemical reactions. All right, so the octet rule is that atoms will tend to gain, lose, or share electrons until they're surrounded by 8 valence electrons. This is a bunch of different elements, hydrogen, helium. Hydrogen has one in the outer shell, its first shell. Lithium only has one in its outer shell, which would be its second shell. But these are the noble gases. They have two for helium. Remember, the very first shell can only hold 2 electrons. Neon, argon, they have 8 in the outer shell. So atoms want to gain, get rid of, get or lose, get rid of electrons or share electrons until they are surrounded by 8 electrons in that valence shell. So a chemical bond is that transfer, gaining or losing, or sharing of electrons that results in a full valence shell. That's what a chemical bond is. And you have ionic bonds, which are good bonds, but they're weak, kind of like Velcro. Covalent bonds, which are great bonds and very strong, like 2 ropes being tied together. And metallic bonds, in which all the atoms share all the electrons. So the electrons are actually moving around. So ionic bonds, electrons are transferred. When one atom loses or gains one of its valence electrons, ions are formed. So it gets rid of it or it gains it, so it's an ion. Now it's not exactly like the other elements other atoms of that element. It has a positive or negative charge. It's an ion. When electrons are lost, it becomes a positive ion. When electrons are gained, it becomes a negative ion. Ionic bonds form when ions with opposite charges are attracted. So you've got a positive ion over here and a negative ion over there. The opposites attract, their opposite charges attract. And when they do attract, they bond together in an ionic bond. They create a compound. Okay? Ionic compounds have very different properties than the bonded elements that make them up. For instance, sodium chloride, that's table salt. Sodium chloride is halite, it's just salt, it makes rock salt. Sodium chloride. Well, sodium by itself is soft, it's a silver, it's a toxic metal. Sodium by itself can react explosively if exposed to water. Chlorine is a poisonous green gas. It was used as a chemical weapon in World War I. But together they make salt, table salt, which is not poisonous or reacts explosively with water. So the separate elements that are looking to bond together have very, very different properties when they are bonded together. All right, so this is how sodium and chloride bond. You've got your sodium atom over here. It has 11 electrons and 11 protons. So it has 2 electrons in the first shell and then 8 electrons in the second shell and then 1 all by itself in the third shell, all right? But chlorine, 2 in the first shell, 8 in the second, that's 10, and then 7 in that outer shell. So sodium has 1 in the outer shell, chlorine has 7 in the outer shell. So if that 1 outer electron goes over to chlorine, then it's stable, meaning the sodium becomes stable, and the chlorine becomes stable because its outer shell now has 8 electrons, and its outer shell has 8 electrons. But in order to do that, it loses an electron, this gains an electron, this becomes a positively charged ion because it loses an electron, this becomes a negatively charged ion, the chlorine because it gains an electron, and then those two stick together because they have an equal positive or negative charge. And they stick together, and there's your chemical bond, and then you have table salt. A covalent bond occurs when when atoms share electrons. So hydrogen only has 1 electron in its first shell, its outer shell, so it's not stable. So it wants to share that electron with something else. So it's very easy to share it with another hydrogen atom, okay? And so this 1 electron and this 1 electron are shared by both. Now you have the nucleus of the first atom, the nucleus of the second atom, each have 1 proton, and they're sharing 2 electrons, and so you have a stable molecule. These are atoms. This is a molecule, H2, which is how hydrogen is actually found in nature. The gas is H2, same with O2. A different bond that you may be more familiar with is H2O. And in that situation, these H2s then share those 2 electrons with oxygen, and it creates a stable, let's find it here. Let's see, where's oxygen? Oxygen is here. And so in its outer shell, it has 1, 2, 3, 4, 5, 6. So it needs 2 more electrons to become stable. So if you take 2 hydrogen atoms, like these 2 here in H2, those 2 electrons can also be shared with oxygen, and you get H2O. Because again, oxygen has 6 electrons in its outer shell. It can share those two electrons. It's not a negative or positive charge, so it's a covalent bond. And the covalent bond between atoms of hydrogen making hydrogen molecule, or the covalent bond between this hydrogen molecule and an oxygen atom, create a very strong bond. It's called the hydrogen bond. It's very, very, very strong. And the bond between H2 and O of H2O is very, very strong. All right. Metallic bonds, a little bit different form. When valence electrons are free to move from one atom to the other, all atoms share available valence electrons, and the movement of valence electrons around atoms results in what makes metals so highly electrically conductive, malleable, meaning they can be squished and moved, and it also gives them other unique properties, the metals, the metallic bond. All right, so one of the other properties of minerals is that minerals have a definite crystalline structure and a definite chemical composition. It gives them their unique physical and chemical properties. Physical properties of individual samples may vary somewhat due to impurities and defects. So the properties of minerals create both diagnostic properties and ambiguous properties. The diagnostic properties are very helpful in identifying minerals, and the ambiguous properties are the type of properties that vary among specimens of the same mineral. So like color. Color is an ambiguous property. You can have a quartz crystal that's clear, white, yellow, pink, and so you can't just use the color to say it's quartz. It's an ambiguous property. Whereas a diagnostic property like cleavage or fracture can be used, or hardness can be used to diagnose which type of mineral it is. So one type of those properties, the optical properties, how it looks. Luster is a type of optical property, and luster is how light is reflected from the surface of the mineral. Minerals that look like they have a shiny metallic have a metallic luster. A non-metallic luster is when they're glassy or dull, or earthy or pearly or silky or greasy. That's a non-metallic luster. So color, again, is very conspicuous, but it's only a diagnostic property for a couple of different. There's some elements that, like sulfur is always green, right? Because it's green. But fluorite and quartz can have the same color. You can have yellow or pink fluorite, a purple fluorite, and purple quartz as well. And so you can't determine between the two because the slight impurities may change the color. You can't determine what type of mineral that is. Streak is the color of a mineral in its powdered form. So if you can make a mineral into a powder, the color of that powder is actually a pretty good diagnostic property. In order to make a mineral, a solid mineral, into a powder, you can rub it against a sample of unglazed porcelain. Unglazed porcelain, pretty rough, it's called a streak plate, and that streak is pretty consistent. So metallic minerals generally have a dark streak, non-metallic minerals have a light streak. Not all minerals, unfortunately, produce streaks, so you can also tell what type of mineral it is if it doesn't produce a streak. So here's pyrite. It's a mineral, you rub it against it, it gives a nice black streak. So the color may not be helpful in identification. The streak is oftentimes very helpful in identifying different minerals. Another optical property is the ability to transmit light. They're either opaque, translucent, or transparent. Minerals that are opaque don't transmit light. Minerals that are translucent will transmit some light, but they don't transmit an image. And minerals that are transparent can actually transmit both light and an image. So knowing what types of minerals are transparent or translucent or opaque can help identify a mineral. The shape, which is also known as habit, is also of the crystal. The crystal shape, also known as the habit, is a characteristic shape of individual minerals or aggregates of those minerals. So most minerals grow into one common shape. Some may have two or more characteristic shapes. So crystal shape is good at identifying, but it's not always perfect. For instance, pyrite can be either little boxy things, as you see on the right, or they can be these little six-sided crystals that you see on the left. Both are pyrite, so you may have to use streak or some other characteristic to know exactly what mineral that is. Different crystal shapes. You have fibrous, you've got bladed, you have banded, and you have cubic crystals. Lots of different different crystal shapes. All right, a really good property of minerals that you can determine their strength, what mineral it is strength, because talc and gypsum is very, very soft, and you can know it, where diamonds are very, very hard, right? So mineral strength determines how minerals break or deform under stress. Hardness is a mineral's resistant to abrasion or scratching. Hardness is measured on a scale from 1 to 10. It's the Mohs scale. It can be determined by rubbing the mineral against a material of known hardness. So a fingernail has a hardness of about 2.5. So minerals with hardness of less than 2.5 can be scratched with a fingernail. Minerals of hardness harder than 2.5 will scratch a fingernail, all right? Glass has a hardness of 5.5, so glass can actually scratch copper, but copper can't scratch glass. And then minerals that are harder than 5.5 will actually scratch glass. All right, so there's that Mohs scale where diamonds are the hardest, talc or gypsum are the weakest, and you can see like quartz is pretty hard stuff. It's not going to scratch very easily. It's also not going to, because it's pretty hard stuff, it's also not going to erode very easily. And topaz and diamonds don't erode at all. They pretty much stay in their solid state. And so you can see how you can use different types of materials to determine the hardness of a mineral, and that can help you determine which mineral it is. And by the way, talc or gypsum is not 2 times harder than talc. It's a logarithmic or a geometric scale. You can see that diamonds are actually 80 times more stronger than talc, even though it's only 1 to 10. It's actually 80 times stronger. All right. Mineral strength also determines its cleavage. Cleavage is the tendency of the mineral to break along planes of weak bonding. So on the right, you see these little dots. That's different silica, and the silica where the kind of the pinkish connects with the blue, that's the silica tetrahedron, and that's a very strong bond. But where the different silica tetrahedrons are bonded together by that red molecule, it's a very weak bond. And that weak bond allows minerals to break, and they break along planes. And so in the case of this particular mineral, it breaks along this one plane. You can pass a knife blade through it, and you get sheets, and that's a very specific type of cleavage. It has one cleavage plane. Now, not all minerals have cleavage, but a lot of minerals do. So it can be easily confused with crystal shape. It's not. Its cleavage is only visible when the mineral is actually broken. Crystal shape is visible whether it's broken or not. All right, here's cleavage in one direction, those sheets, cleavage in 2 directions, that's 90 degrees, creates that 90-degree break. Cleavage in 2 directions that's not at a 90-degree angle creates these angled. You get cleavage in 3 directions, which creates cubes. Cleavage in 3 directions not at 90 degrees, which creates these little sideways, and then cleavage in 4 directions creates something like fluorite. So you can see how cleavage will break a mineral will break into these very different shapes. Fracture results from chemical bonds that are approximately equal in strength. So you have either irregular fracture, which is uneven and broken, or conchoidal fracture, which is smooth and curved. And you can see the two. Quartz has a regular fracture, where this other type of quartz has a more conchoidal fracture. So different types of fracture are found in different minerals as well. That's a property that can help identify the mineral. Tenacity is the mineral's resistance to breaking, bending, or cutting. So harder minerals have harder tenacity. So minerals with ionic bonds, which we said are weaker, they tend to shatter. Native minerals, that metallic bond creates them malleable. They don't break easily, they bend. And then, different minerals are going to have different resistance to breaking, and that's their tenacity. And it's also a way that you can identify a mineral. Specific gravity basically is the density of a mineral, and the ratio of the mineral's weight to the weight of an equal amount of pure water. Most minerals have a specific gravity between 2 and 3. Those metallic minerals, much higher specific gravity because they're much denser, and other minerals may be somewhat lighter. You basically can pick up a mineral in your hand and tell whether it's heavy or light. So some specific minerals have some very distinctive properties that make them very easy to determine. If you're willing to put your tongue on a rock, you may taste it as being salty. Well, that's halite, that's sodium chloride, that's salt. Talc, which is a mineral, is very soapy. Graphite, like in pencils, is very greasy. Sulfur not only is green, but it smells like rotten eggs. Magnetism, some minerals have magnetic properties. Some minerals have optical properties, and some minerals like carbonate or calcium carbonate actually fizz in weak solution. So if you have a rock and you're trying to figure out what it is, you can put a weak solution of acid on it, and if it fizzes, then you'll know it's a carbonate mineral. And there's your refraction going on and your fizzing happening as well. All right, there are over 4,000 named minerals, but only a few dozen are abundant in the Earth's crust, and those are known as rock-forming minerals. There's also economic minerals that are less common than rock-forming minerals, but are used extensively in some manufactured products. The majority of rock-forming minerals are made up of only 8 elements: silicon, Si, oxygen, O, that's obviously the bulk of them. You got aluminum, pretty big chunk of aluminum in the crust, calcium, sodium, magnesium, potassium, and iron. So there's 1.5% of all crustal rocks that are something else. 98.5% of all crustal rocks are made of these 8 elements, and of course you can see that some 70-80% of all crustal rocks are made up of silicon and oxygen, that silica tetrahedral that I described a few minutes ago. There are silicon and oxygen combining together to form the basic building block for the silicates. So the silicates are a type of rocks that make up most of the rocks. Lots and lots of silicates out there. The basic building block of silicates is a silica tetrahedron, in which silica, which is a small atom, is surrounded by oxygen, and the silica has a +4 charge and the oxygen has a -2. So there are, that gives it a charge itself, but they stick together. It causes them to stick together in this tetrahedra, which gives it its classic crystalline shape. But there's a huge amount of silicates. The most common mineral, there's 800 different types of silicate minerals that make up 90% of the Earth's crust. And those silicate minerals occur when these silicon tetrahedrons are bonded together with other elements. The remaining mineral groups are often referred to the non-silicates. Clearly, they're far less abundant, but some of them make important economic minerals. All right, so maybe tough to see, but one of the things I want you to notice about the common silicate mineral groups is if you look at the top, you have individual single tetrahedra that make up that olivine group. And you have very simple silicate structures, just that simple tetrahedra, all right? That is a low silica rock. There's not much silica in that rock. If you go down to the bottom, you can see those tetrahedra are grouping together in these very complex three-dimensional network, and those rocks have a great deal of silica in them. And this is going to become very important when we start talking about magmas and volcanoes and different types of rocks. The chemical composition of rocks is largely determined by how much silica. A little bit of silica or a lot of silica. And as you can see, those rocks at the top that only have a little bit of silica tend to be darker, and the rocks at the bottom that have a lot of silica tend to be lighter. And we're going to come back to silica content over and over again. So 4 oxygen atoms, covalently, they share electrons with the much smaller silicon atom. And then because you have 4 oxygen atoms with a -2, that's -8, the silica has a +4, so the overall charge of that tetrahedra is a -4, and that allows that tetrahedra to very easily ionically bond to lots of other elements, and that's how you get those silicate groups. The tetrahedra themselves can also be joined into chains, as you can see with the pyroxene, sheets, as we can see with the amphibole or the biotites, the muscovites, and then you can also have much more complex three-dimensional networks. All right. The feldspars are the most plentiful silicates, about half the Earth's crust. The quartzes are the second most abundant minerals in the crust. So the feldspars are here. A lot of silica, light and colored, and the quartzes are beneath them, and they make up most of the Earth's crust. Silicate minerals tend to cleave between those strong silicon-oxygen structures. So the silicon-oxygen tetrahedra doesn't cleave. It's the bond between them where it cleaves. Most silicate minerals crystallize from molten rock as it cools. So most of our silicate minerals will crystallize from molten rock as it cools. So as the magma cools, it crystallizes into silicate minerals. And it really depends on the environment and the chemical composition that determines which minerals are actually produced. Some silicate minerals form at the Earth's surface as other silicates are weathered. So you may get a silicate mineral that occurs because some rock is weathered, and that weathered material is transported somewhere else and then reforms as a sedimentary rock that's a silicate. And then other silicate minerals form at extreme pressure during mountain building. So those that form silicates that form from weathered material are sedimentary rocks, and those that form from extreme pressures are metamorphic rocks. So your silicates are largely igneous, but some can be sedimentary, and some can also be your metamorphic.
Now, generally, we have two types of silicate materials. We have light silicates and dark silicates. Your light silicates are going to include feldspars, quartz, muscovite, clay materials, those silicates that have aluminum, potassium, calcium, and perhaps some sodium in them. You also are talking about feldspars being the most abundant of the silicates. They're found in igneous, sedimentary, and metamorphic rock. A couple of details about them: 2 degrees of cleavage at 90 degrees, so a 90-degree cut, 6 on the Mohs scale. Your potassium feldspar does contain some potassium, so we have different types of feldspars with containing different elements that give them different, at least different colors and different chemical composition. Quartz is silicate material, and of course it is common in igneous rocks, also sedimentary and metamorphic rocks. The impurities cause different varieties of colors. It's a little bit harder. It has hexagonal crystals with pyramid-shaped ends, and if it's broken, it exhibits that conchoidal fracture. It's got that curved, smooth plane if it's broken. Muscovites are, remember, that mica family. They have one cleavage plane, so they come off in sheets, as you can see with the knife blade going through the mineral to the right here. And again, the silicon tetrahedral is here, and you don't have a cut across the tetrahedral. It's between them. These weaker bonds is where you cut it into these flat sheet plates. Now, clay minerals are commonly the weathering products of silicates. When silicates are exposed to water, hydrogen ions will replace the ions in the silicates, and you get chemical weathering. The rock is broken down at the surface in the presence of water, and the result is often different types of clay minerals, and those clay minerals are common parts of soil and make up nearly half of the volume of sedimentary rocks. That's what clay materials do. So the other type of silicate I mentioned is the dark silicate minerals. They contain iron and magnesium. Partial list here: olivine, garnet, of course, dark color and high specific gravity because they have a high iron content, so they tend to be heavier. Olivine is a major constituent of dark igneous rocks, abundant in the Earth's upper mantle. It's black to olive green color, glassy luster, and granular. There's pyroxenes. They're an important component of dark colored igneous rocks as well. The amphibole group includes minerals that commonly make up the dark portion of light colored rock. So you'll have a light colored rock with little dark parts in it. Those would be the amphiboles. So again, you have your light and your dark silicate minerals. Here are some of those dark silicate minerals: the olivine, the augite, the hornblende that you can see. Biotite is that mica, is that flat sheet-like rock, is an iron-rich member of the mica family. That's that cleavage in one direction. And you oftentimes find biotite in other light-colored rocks, like in your granites and garnet is a dark silicate. All right. Also, we have lots and lots of silicate and crustal rocks, but we also have non-silicate materials. And the non-silicates are divided into groups based on the negatively charged ion that is actually common to that group. So non-silicates make up about 8% of the Earth's crust. They occur in significant amounts in sedimentary rocks, and of course some of those non-silicates are economically valuable. So one of those groups is the carbonate group. It has the CO3, the negative ion of CO3, and you find those in calcite and in dolomite, cement, building stone like marbles, and also used to help build roads. Halite and gypsum are non-silicate materials that are evaporite. So halite is basically table salt. When salt water evaporates, it can leave behind sodium chloride in the form of halite, or gypsum, which is a sulfate. Gypsum is used in building materials like plaster and sheetrock. Oxides are important in iron ores because they actually attack the irons. And then you have these other economically important non-silicate minerals, sulfides, and golds and silvers and coppers, fluorites, and different things like that.
So that's going to wrap up chapter 1. Not bad, right? Less than an hour. That's Foundations of Earth Science, the 8th edition by Electrons and Tarbuck, Matter and Minerals, chapter 1. So we'll be taking a look at chapter 2 coming up on the next lecture, the next YouTube lecture. So join me for that. We'll be talking about rocks and the materials of the earth. So we'll see you then.